Hello and welcome, guys, to the Cyber Diaries episode 4. Today we'll discuss the second part of our Kubernetes deep dive. So, in the first episode, we covered some of the important topics around cloud native security, defense, and depth. So, we covered 4 C's and how we secure our clusters, containers, cloud, and the code itself. And today we're going to dive a bit deeper into various controls that we have at our disposal to ensure the security of Kubernetes clusters. So we look at things like pod security standards, as covered in this slide. We'll look at security context. We'll look at networking policies, as well as we'll cover some of the security checklist, which potentially is not exhaustive list, but it's a way to understand that. I think, as I covered sort of in a first episode, I think it's very important to understand the vast controls that Kubernetes have, and in order for them to be secure, I think, as we all know, most of the organizations nowadays are shifting towards the cloud environment and potentially leveraging platform as a service, which is Kubernetes is part of. So just understanding and knowing where the potential pitfalls are within the Kubernetes clusters, how we need to secure them to prevent data exfiltration, to prevent secret leakage, and all of that. So this is what this episode is all about. So let's dive right into pod security standards. So pod security standards kind of define 3 different policies that kind of broadly cover the security kind of spectrum within it. So these policies are cumulative, so it's very important to understand that they essentially range from highly permissive to highly restrictive. So essentially, first of all, we have a privileged policy. So privileged policy is purposely open and entirely unrestricted. So the type of policy is typically aimed at system and infrastructure level workloads and managed by privileged and trusted users. So the privilege policy is defined by, essentially by an absence of restrictions. So allowed by default mechanisms such as, gatekeeper may be privileged by default. In contrast, for a denied by default mechanism such as pod security policy, the privilege policy should disable all restrictions. Next one, we move into the baseline policy. So the baseline policy is aimed at essentially ease of adoption for common containerized workloads while preventing known privilege escalations. So the policy is targeted at application operators and developers of non-critical applications. So essentially, there is a list of privileges and controls that are allowed within the baseline. So it's essentially it's the first way of essentially it indicates and there is a list. Any of you guys can Google or jump into Kubernetes documentations because it's too long to list there. But there's a list of essentially within spec containers security context that refers essentially to each object defined within the containers which are allowed in the baseline. And then the last one, we have a restricted policy, which is essentially aimed at enforcing the most common, essentially current pod hardening practices. So essentially, at some point, to the expense of compatibility. So it is targeted at operators and developers of security critical applications as well as the lower trusted users. So I think it's important to note, those of you who are aware of, and we're going to dive into security context and how we can define, capabilities that are allowed in our pods, how we can define, sort of root level access, root level permissions within our pods. So essentially, I think what they've done with the pod security standards essentially is grouped a number of those contexts and sort of permissions and sort of things essentially within the pods that are allowed into sort of 3 profiles essentially. Instead of you defining a context one by one, it gives you a broad spectrum of, how you can define essentially your policies and apply this policy. So if we go into the next one, so I think another important point is to understand how, most of the pods, if they're running any specific workload or completing any specific task, they will have a service account. So how we secure and how we use the service accounts is very important. So essentially, a service account is a non-human account that in Kubernetes provides a distinct identity in a Kubernetes cluster, essentially. So any application, pods, system components and entities inside and outside the cluster can use a specific service account, essentially credentials, to identify, as that service account. So the identity is useful in various situations, including authenticating to the API server or implementing identity-based security policies. It's important to note that service accounts exist as service account objects in the API server, and service accounts have two main essentially properties. So they are namespace and they are lightweight. So basically what I mean by that, so namespace, essentially each service account is bound to a Kubernetes namespace. So every namespace gets a default service account upon creation, and then obviously you can define your own service accounts based on the workloads that you are creating. So it's very important to know that they are namespace. So every service account that you create, and in order to use in various pods, you have to create that in that specific namespace where your pods or containers are running. It is also lightweight. So a service account exists in a cluster as essentially and now defined in a Kubernetes API, which you can quickly create service accounts to enable specific tasks. And then last but not least, they are portable. So a configuration bundle for a complex containerized workload might include service account definitions for the system components. So the lightweight nature of service accounts and the namespace identities make the configurations portable. So service accounts are different from user accounts. That's very important to know, which are essentially authenticated human users in a cluster. So by default, user accounts don't exist in Kubernetes API server. Instead, the API server treats user identities as opaque data. So you can authenticate as a user account using multiple methods. So some Kubernetes distributions might add, custom extensions to the APIs to represent user accounts in the API server. So let's dive into let's discuss a bit about default service accounts. So when you create a cluster, essentially Kubernetes automatically creates a service account object name default for every namespace in your cluster. So the default service accounts in each namespace gets no permissions by default other than the default API discovery permissions that Kubernetes grants to all authenticated principals if role-based access control is enabled. If you delete the default service account object in the namespace, the control plane replaces it with a new one. So there's always going to be a default service account. Whether you delete it, the control plane has an automatic job to create a new one. So if you deploy a pod in a namespace and you don't manually assign a service account to the pod, the Kubernetes assigns the default service account for that namespace to the pod. So it's important, to know, as a general guideline, you can use service accounts to provide identities in the main following scenarios. So your pod needs to communicate with the Kubernetes API server. So in those, for example, scenarios like providing read-only access to sensitive information stored in the secrets, or granting cross-namespace access, such as allowing a pod in the namespace example to read, list, or watch for lease objects in the kubenode lease namespace. Your pods also need to communicate with an external service. So for example, a workload pod requires an identity to commercially available cloud API, and the commercial provider allows configuring a suitable trust relationship, authenticating to a private image registry using the image pull secret permissions, an external service needs to communicate with the Kubernetes API server. So for example, sometimes you need authenticating to the cluster as part of the CI/CD pipeline. You also might use it for third-party security software in your cluster that relies on the service account's identity of different pods to group those pods into a different context. So how do we use the service accounts? So, to use a service account, you must do the following. So you create a service account object using Kubernetes client, such as, kubectl, or a manifest essentially that, defines the object. So you need to grant the permissions to the service account object using an authorization mechanism, such as role-based access control. You need to assign the service account object to pods during pod creation. And if you're using the identity from external service, you need to retrieve the service account token and use it from the service instead. So as you can see, for example, there's a very simple example of the service account below. So there's a YAML file that, you were obviously API version 1. So we have defining the kind of the object, which is a service account. We can create a metadata annotation, which obviously this one says that it's enforcing the mountable secrets, which is true. And then you have to name the service account, which is in this case is a my service account. And then you have in which namespace the service account is going to be located, which is my namespace. So those of you obviously who just starting out, you need to understand how namespaces are defined. Namespaces are usually you can sort of, it's an opaque thing that you can define how you're going to store your pods or your containers. So essentially you can separate specific namespace containers. So if you, for example, if you're creating specific, applications, maybe you want to group, backend pods into backend namespace, or, specific, if you are creating specific application, you can separate things by namespace. So that's a good way, to kind of, it's a good practice to separate your workloads via namespace. I think important thing to note as well is you can use the built-in Kubernetes role-based access control mechanism to grant the minimum permissions required by each service account. So you can create a role which grants access and then bind that role to the service account. So role-based access control lets you define minimum set of permissions so that service account permissions follow the principle of least privilege. That's very important to know. When we're creating roles and then we bind them to service account, we need to make sure that those roles only have the needed permissions that we define for this service account. We need to make sure that they don't have more permissions that are required to function correctly. So let's jump into the next one. So this is the port security admission. So the Kubernetes port security standards essentially define different isolation levels for the pods. So these standards let you define how you want to restrict the behavior of pods in clear and consistent fashion. So Kubernetes offers a built-in pod security sort of admission controller to enforce the pod security standards. So pod security restrictions are applied at the namespace level when the pods are created. So essentially, pod security admission is started, I think, from Kubernetes version 1.28. So, all of this is taken for the current version of Kubernetes. So pod security admission places requirements on the pod security context and other related fields according to the 3 levels defined by the pod security standards. So we just discussed those in the previous slides, which is you have 3 standards. So you have the privileged, you have the baseline, and you have a restricted standard. So once the feature is enabled, or the webhook is installed for the pod security admission, you can configure namespaces to define the admission control mode you want to use for pod security in each namespace. So Kubernetes essentially defines a set of labels that you can set to define which of the predefined pod security standard levels you want to use for your namespace. So, essentially the label you select defines what action the control plane takes if potential violation is detected. So I guess it's important to know that these two kind of work hand in hand. So you have pod admission security policies, which we just kind of discussed in the first slide, where you have three defined policies, and essentially this pod security admission defines what we do. So are we just warning? So we're creating essentially violations to trigger user-facing warning. Are we auditing? So essentially we triggering additional audit annotation to the event recorded in an audit log. Or we actually enforcing the violations, and essentially we will reject the pod in its creation. So it's important to know that essentially it is always enforced at the pod creation time. So pods are often, created directly by creating a workload object, such as, deployment or a job. So the workload object defines a pod template, and a controller for the workload resource creates pods essentially based on that template. So to help catch violations early, both the audit and warning modes are applied to the workload resources. However, enforce mode is not applied to the workload resources, only to the resulting pod objects. And there are a few exemptions. So you can define essentially exemptions as well for pod security enforcement in order to allow the creation of the pods that would have otherwise been prohibited due to the policy associated with a given namespace. So exemptions can be statically configured in the admission controller configuration. But it's important to know that exemptions must be explicitly enumerated. So requests meeting the exemption criteria are ignored by the admission controller. All enforce, audit, and warn behaviors are skipped. So essentially, exemption dimensions can be included, such as, so you can create usernames. So requests from users with an exempt, authenticated, or impersonated username are ignored. You can ignore runtime class name, so pods and workload resources specifying an exempt runtime class that are ignored. You can ignore the namespaces, so pods and workload resources in exempt namespace are ignored. And caution, so most pods are created by a controller in response to the workload resource, meaning that exempting an end user will only exempt them from enforcement when creating pods directly, but not when creating a workload resource. So controller service accounts such as system service account, kube system, replica set controller should generally not be exempted, as doing so will implicitly exempt them from any user that can create the corresponding workload resource. So updates to the following pod fields are exempt from policy checks. So meaning that if a pod update request only changes these fields, it will not be denied even if the pod is in violation of the current policy level. So any metadata updates except changes to the SecOmp or AppArmor annotations. So Cyber Security Alpha Kubernetes.io pod, these are, will not throw a violation, and they are getting deprecated now. I think another important note is that container.apparmor.security.beta.kubernetes.io will not throw a violation. Valid updates to spec active deadline seconds. Valid updates to the spec tolerations will not throw a violation. So that's important things to know. So yeah, so this is essentially, you have two examples here. So you have the description of the three ways how we can enforce it, And then obviously we have a way how we can configure that in our YAML file. So as you can see, you have pod security kubernetes.io, and then you can create essentially a mode and a level. And then you can essentially, as you can see, so in the mode you define essentially the level. So mode is essentially a way to enforce, audit, or warn against specific policy violations, and then the level are defined as privileged, baseline, or restricted, as mentioned in our first slide. So let's move on to the next one. So network policies. It's another very important part. Is I think people always miscomprehend how to use and when to use network policies. So it's very important to know that when you're creating pods in Kubernetes clusters, essentially from the get-go, every pod can communicate to every pod. So if you imagine, like, if one pod in your Kubernetes cluster, so sometimes, clusters can expand into hundreds of pods, even probably thousands. So if one pod is breached, essentially the threat actor can access every single pod within the cluster. So it's important to create definitions and limit essentially the blast radius of which pod can communicate to what pod. So you can create, specific tags, and we can create ingress and egress essentially policies that tells us who the pod can accept traffic from and where they can send the traffic to. So, essentially, if you want to control the traffic flow at the IP address level or port level for the TCP, UDP, or even SCTP protocols, then you might be considering Kubernetes network policies for particular applications in your cluster. So network policies are an application-centric construct which allows you to specify essentially how the pod is allowed to communicate with various network entities. So we use word entity here to avoid overloading more common terms such as endpoint services, which have specific Kubernetes connotations. So over the network. So network policies apply to a connection with a pod on one or more, essentially both ends, and they're not relevant to any other connections. So entities that a pod can communicate with are identified through a combination of the following, essentially 3 identifiers. So other pods that are allowed, exception, pod cannot block access itself, to the namespaces that are allowed, and to the IP blocks. So when defining a pod or namespace-based network policy, you need to essentially use a selector to specify what traffic is allowed to and from the pods. So as you can see in the first example here, you can create a namespace selector. So you can see, for example, we are defining an ingress traffic network policy. So we create an ingress and we say from, so where the traffic is coming from, and then you can define by namespace selector or pod selector. So you can create namespace selector, then you create the match labels, and obviously it's a key pair to identify the namespace. So you need to make sure that you create a key value pair to identify your namespaces as well as pods. So then the second one is pod selector, match labels, role, and the client. So that's the key pair to identify the pods. So essentially what you're doing now, you're creating a network policy that will allow traffic from the whole namespace called Alice, as well as from any pod that has a role attached to it, client. So meanwhile, the IP-based network policies are created. We define essentially policies based on IP blocks or CIDR ranges. So there is a few prerequisites that we need to understand. So network policies are implemented by the network plugin. So to use the network policies, you must be using a network solution which supports network policy. So creating a network policy resource without a controller that implements it will have no effect. So there are 2 sorts of pod isolation for a pod. So essentially isolation for egress and isolation for ingress. So egress is obviously it's outward traffic and ingress is traffic coming in. So they concern what connections may be established. So isolation here is not absolute. Rather, it means that some restrictions apply. So the alternative, non-isolated for direction, means that no restrictions apply in the stated direction. So two sorts of isolation or not are declared independently and are both relevant for a connection from one pod to another. By default, a pod is non-isolated for egress, so all outbound connections are allowed. A pod is isolated for egress if there is any network policy that both selects the pod and has egress in its policy types. So we say that such a policy applies to the pod for egress. So when a pod is isolated for egress, the only allowed connections from the pod are those allowed by egress list of some of the network policy that applies to the pod egress. So the effects of those egress lists combine additively. So you need to understand that they accumulate in the list. So by default, a pod is non-isolated for ingress. All inbound connections are allowed. A pod is isolated for ingress if there is any network policy that both selects the pod and has ingress in its policy types. So I guess that's the kind of the important things to know. For a connection from a source pod to a destination pod to be allowed, both egress policy on the source pod and the ingress policy on the destination pod need to allow the connection. So that's a very important thing to know as well. So guys, if you create two pods, so in order for pods to communicate, so say the left pod has to have an egress policy that allows communication to this pod, and then this pod has to have an ingress policy that allows the connection from the previous pod. So it's a two-way street. You can't just open up one policy and then the pods will communicate. So it has to have a definition for ingress and egress on both ends of the communication. It's also important to note, so there are some mandatory fields that each network policy should have. So you should always have a spec. So network policy spec has all the information needed to define a particular network policy in the given namespace. You have to have a pod selector. So each network policy includes a pod selector which selects the grouping of pods to which the policy applies. So, we have an example here as I, showed. So pod selector, match labels, and obviously we have a role client. You have to have a policy type. So each network policy includes a policy type list, essentially, which may include egress, ingress, or both. The policy type field indicates whether or not the given policy applies to ingress traffic to selected pod or to egress traffic. So that's an important thing to note and to understand. It also has to have ingress. So when you define ingress, you should define traffic which matches both the from and the ports sections, and also the egress. So each network policy may include a list of allowed egress rules. So each rules allows traffic which matches both the to and the port sections. So it's important to know the behavior of to and from selectors. So there are four kinds of selectors that can be defined in ingress section or egress section. So you have pod selector, so it selects specific pods. You have namespace selector, which selects specific, namespace. You also have a namespace selector and pod selector, so you can select specific namespace and specific pod in that namespace. And then by default, if no policies exist in a namespace, then all ingress and egress traffic is allowed to and from pods in that namespace. And that's as I just mentioned. So the way you normally define the network traffic in your namespaces, as you can see, there is an example on the bottom. So what you normally, the best practice is you define a default ingress policy. So essentially you create a policy that disallows all of the ingress traffic, and then you just whitelist the allowed traffic. So this way you have a defined way of what is allowed in. So as you can see, you have an API version. Obviously we have networking. You have a kind metadata, which is obviously the network policy. So obviously we define the policy name, which is default deny ingress. And as you can see, we have a spec. So when we do a pod selector, we have a curly brackets. So basically means that we are selecting every single pod in that namespace. And we have a policy type of ingress. So since we're not defining any ingress rules, then basically we are blocking the traffic by default. And let's jump into the next one. So let's kind of cover the security context. So I kind of covered a bit about, and we talked about admission policies. So, I kind of mentioned to you guys that, the policies defined in admission control, they essentially are grouping those security contexts into 3 easy to use profiles or essentially policies. But you can define very fine-grained security context by yourself, and we can kind of showcase some of the stuff here. So essentially, what security context is it essentially defines privilege and access control settings for a pod or container. So security context, settings include but are not limited to, stuff like discretionary access control. So permissions to access an object like a file is based on, user ID, UID or group ID, so GID. We also can define security enhanced Linux, so SE Linux objects to specific security labels. We can define whether the container can run as privileged or unprivileged. We can define specific Linux capabilities, so give a process some privileges, but not all privileges to the root user. We can also define AppArmor, so using a program files to restrict the capabilities of individual programs. We can also use a seccomp, so we can filter processes system calls. So seccomp is a great way as well to essentially limit process calls to the kernel and what can be called to the underlying kernel, essentially underlying a platform that runs the containers. We can allow privilege escalation, so we can define whether privilege escalation is allowed or not. So we can also define, essentially, it's we can define basically this is a boolean with directly controls whether there's no new privilege flag set on the container process. So allow privilege escalation is always true when the container is running as privileged, or you allow it cap sysadmin capabilities. You can also define whether read-only root file system. So essentially, you mount the container root file system as read-only. So these are essentially the main controls that we can have. So you need to have Kubernetes cluster and the kubectl command line tool. And essentially it must be configured to communicate to your cluster, and then you can create those controls essentially. So to specify a security settings for a pod, you must include a security context field in the pod specification. So the security context field is pod security context object. So security settings that you specify for a pod apply to all containers in the pod. So as you can see, we have a configuration file on the left side. So as you can see, we're creating a YAML file for a pod, which obviously it's named as security context demo. So there is a few ways we can define. So we are defining, for example, security context. So we can define, for example, by default, pod is going to be running as root. So, but also we can define, so in that security context, we're defining, so run as user 1000. We can also run as group 3000 and FS group 2000. So we define that essentially this pod is not going to run as root. We can also, as you can see at the very end, define the actual container security context. So as you can see, allow privilege escalation flag is set to false. So that means that this container is not able to escalate its privileges. So that's another important thing to note and to understand how we can do that. So for example, as you can see in the configuration file, run as user field specifies that for any container in the pod, all processes will run as user ID 1000. The run as group field specifies the primary group ID of 3000 for all processes within any containers in that pod. And if the field is omitted, the primary group ID of the container will be root 0. And then also, any files created will also be owned by user 1000 and group 3000. When run as group is specified, so that's an important thing to know. And then since FS group field is specified, all processes of the container are also part of the supplementary group of ID 2000. So the owner for the volume data demo and any files created in that volume will be group ID 2000. We also can configure volume permissions and ownership change policy for the pods. So by default, Kubernetes recursively changes ownership and permissions for the contents of each volume to match the FS group specified in the pod security context when that volume is mounted. So for large volumes, checking and changing ownership and permissions can take a lot of time, slowing essentially a pod startup. So you can use the FS group change policy field inside the security context to control the way that Kubernetes checks and manages the ownership and permissions of a volume. So essentially the FS group change policy defines behavior for changing ownership and permissions of the volume being created and exposed inside the pod. If you deploy a container storage interface driver which supports the volume mount group node service capability, the process of setting the file ownership and permissions is based on the FS group specified in the security context will be performed by the CSI. To specify security settings for a container, include the security context field in the container manifest. So the security context field is a security context object. So security settings that you specify for a container apply only to the individual container, that they override settings at the pod level. So as you can see on that file, on the YAML file on the left, we have a spec security context for a pod, and we also have security context for specific containers. So you can define at the pod level, which essentially applies to every single container, or you can override for a specific container. So security settings that you specify for the individual container, they will override, as I mentioned. So to get the seccomp profile for a container, you must include the seccomp profile field in the security context. So as you can see on the top right, you have security context, and then you can define the seccomp profile and the type of the profile. And then also, as you can see underneath, you can define security context. And as we covered, you can also define specific SC Linux options. So as you can see, there is a level S0, C123, C456. So you can define specific SC Linux options. So obviously you can read up and understand what specific options and what do they do. So now let's cover AppArmor. So AppArmor is essentially, it's a Linux kernel security module that supplements the standard Linux user group and group-based permissions to confine programs to a limited set of resources. So essentially AppArmor can be configured for any application to reduce its potential attack surface and provide greater in-depth defense. So it is configured through profiles tuned to allow the access needed by a specific program or container, such as Linux capabilities, network access, file permissions, and etc. Each profile can be run in either enforcing mode, which blocks access to disallowed resources, or complaint mode, which only reports violations. So AppArmor can help you to run a more secure deployment by restricting what containers are allowed to do and or provide a better auditing through the system logs. However, it is important to keep in mind that AppArmor is not a silver bullet and can only do so much to protect against exploits in your application code. It is important to provide good restrictive profiles and harden your applications and the cluster from the other angles as well. And that's why we covered, the 4 C's, the defensive in depth. So essentially, the objectives of AppArmor is to essentially to define specific profiles and how we can restrict, specific access to our pods. Important thing to know that AppArmor profiles are specified per container. So to specify an AppArmor profile to run a pod container with, you need to add an annotation. So as you can see on the left side, we have a YAML configuration file for a pod, and then we add an annotation. So annotation is as follows: is you have a container.apparmor.security.beta.kubernetes.io, and then you define the pod. So as you can see, you must, after the slash, you must provide the pod name. So as you can see, pod name is hello. So we define hello, and then we define the policy that we're going to use. So the policy is and its destination essentially. So you have localhost, KAS, AppArmor, example, deny, write. So that's the policy that we define. So write essentially is where the container name is. You have to apply the container name, so that's very important, and that's why we just kind of covered it. Hello, and then obviously you define the AppArmor profile. So you have obviously, runtime default to apply to runtime's default profile, and then you have obviously localhost profile name. So to apply the profile, load it on the host with the same profile name. So Kubernetes AppArmor enforcement works by first checking that all the prerequisites have been met, and then the forwarding the profile selection to the container runtime for enforcement. If the prerequisites have not been met, the pod will be rejected and will not run. So first we need to load the profile we want to use on our nodes, and then, for example, essentially this profile denies all file writes. So as you can see on your right hand side on the bottom, we have created a profile. So we have a profile, we define the name of the profile, which you can see as KAS AppArmor example deny write, and then essentially we define file, and then we define how we're going to deny all file writes. So essentially this profile, when mounted on the pod, it will stop from writing any files. So essentially pod will not be able to create and write files. So it's very simple profile, but obviously you can define various kinds of files, and obviously you need to learn how to create specific AppArmor profiles. Again, you can dive into Kubernetes documentation to understand more, but it's a great way to annotate pods and create restrictions in sort of how we want our pods to behave. And then last but not least, we'll cover the encryption. So it's important to know that obviously all of the APIs in Kubernetes that let you write persistent API resource data support at-rest encryption. So for example, you can enable at-rest encryption for secrets. This is at-rest encryption is additional to any system level encryption for etcd cluster or for the file system on hosts that where you're running the Kube API server. If you want to encrypt data in the file systems that are mounted into containers, you instead need to either use a storage integration that provides encryption volumes or encrypt data with your own application. So the Kube API server process accepts an argument, which is encryption provider config, that controls how API data is encrypted in etcd. The configuration is provided as an API named encryption configuration, and an example is provided below. So as you can see, we have YAML file on the left. So we have an encryption configuration kind file where we define the resources. So we have secrets, config maps, and you have obviously pandas. So then we can create a providers. So essentially we have an identity. So essentially, basically, that means that identity is not encrypted. And then we define the keys that we have for AES GCM and AES CBC, and then secret box. But it's important thing to know that, and as you can see as well, the problem that we have, for example, so secrets are here defined as base64 files or base64 encryption. So that is obviously, if a threat actor gets access to those configuration files, then obviously they can uncover the secrets. That's one problem. And secondly, some of these encryption protocols are not safe. So as you can see on the table on the right hand side, we have CBC is not recommended due to the CBC's vulnerabilities, and the same as GCM, not recommended for use except when an automated key rotation scheme is implemented. So we should always use KMS version 2 or KMS now version 1, which is getting deprecated past the Kubernetes version 128. And then obviously we're going to be moving to KMS version 2, which are the two strongest encryptions. So each resources array item is a separate config and contains a complete configuration. So as you can see, as I mentioned, on the left hand side. So the providers array is an ordered list of possible encryption providers to use for the APIs that you listed. So each provider supports multiple keys. The keys are tried in order for decryption. And if the provider is the first provider, the first key is used for encryption. Also, encryption configuration supports the use of wildcards to specifically the resources that should be encrypted. Use the group to encrypt all resources within a group. So you can use also apps to encrypt all apps, or use a wildcard to encrypt all of the resources. Opting out of encryption for a specific resources while wildcard is enabled can be achieved by adding a new resource array item to the resource name. So followed by the provider's array item and with the identity provider. So for example, if you use a star wildcard is enabled and you want to opt out of encryption for the events resource, add a new item to the resource array with events as the resource name, follow that provider's array with identity. Before you configure encryption at rest for data in your cluster's Kubernetes API, you need to select which providers you will use. So it's important to know, obviously, as you can see on the table on the right hand side, you have a list of providers that you can use for your encryption. It's not enough to make sure that new object gets encrypted. You also want the encryption to apply to the objects that already are stored. So that's one thing to notice. When you create encryption configuration, essentially it will apply only to the new secrets. So for this example, if you have configured your cluster so that secrets are encrypted on write, performing a replace operation for each secret will encrypt the content at rest with the objects unchanged. So that's a very important thing to note, guys, as well. When you create encryption configuration, it will only apply for all the secrets that are created newly. Any of the secrets that you already have stored in your clusters, what you can do is you replace the secrets with a new secret, and essentially then it will be encrypted at rest. Changing a secret without incurring downtime requires a multi-step operation, especially in the presence of highly available deployment where multiple Kube API server processes are running. So if you want to generate essentially a new key, and it has a second key entry for the current provider on all servers, you have to restart the Kube API server processes to ensure that each server can decrypt using the new key. You also have to make sure that the key first entry in the key array so that it is used for encryption in the config. You restart all Kube API server processes to ensure each server now encrypts using the new key, and then you need to run the kubectl get secrets -- all namespaces -o JSON, and then kubectl replace -f to enforce and essentially encrypt all the secrets with the new key. And then you need to remove the old decryption key from the config after you have backed up the etcd with the new key in use to update all secrets. You can also configure automatic reloading of encryption provider configuration. That setting determines whether the API server should load the file you specify for encryption provider config only at the startup or automatically whenever you change that file. So enabling this option allows you to change the keys for encryption at rest without restarting the API server. So that's a kind of fly through of the encryption. We covered quite a few in-depth security configurations, and then I guess we're going to jump into the last video on our 5th episode and cover some of the checklists that you could have to hand if you are working towards deployment of Kubernetes clusters. As always, guys, pleasure to cover and share my knowledge in Kubernetes with you guys. If you wish to connect, discuss any potential topics that we can discuss in the future, or would like to jump and do an interview, you can always reach me via LinkedIn or comment via videos. I'm always here, guys, to help and answer any of your questions. Thank you for your time.